Hello students, welcome to EPG Pathshala. I am Professor P.N. Kodru from Jammu. Today we are going to discuss about a module entitled X-rays, their sources and their interaction with matter under paper crystallography and crystal growth. So students, let us see what we are going to learn in this module. Sources of X-rays, detection of X-rays, ionization of gases by X-rays, interaction between X-rays and matter, and diffraction of X-rays, derivation of Bragg's law, and von Laue equations. Now let us first take up the sources of X-rays. The underlying principle of generating X-rays is to bombard a solid target by fast-moving electrons. According to classical thermodynamics, a moving charged particle emits electromagnetic radiation when it is accelerated. When an electron is suddenly stopped, it results into a pulse of radiation which is in the form of X-rays. X-rays may be produced in a cathode ray tube which is filled with gas at a low pressure. A metal anticathode is placed opposite the cathode, the former being used as a target which receives high-speed electrons emitted by the former and thus serves as the source of X-rays. X-ray sources of increasing efficiency have been devised over a period of time. X-rays are produced by sources like gas tube, the Coolidge tube, the Betatron, and others. Different means of producing X-rays may be summarily described as follows. The gas tube. The gas tube is essentially a cathode ray discharge tube as is shown in a schematic diagram of figure 7.1. C represents concave shaped cathode made of aluminum metal. A is anode which is connected to the target T. The anode is placed inside the tube as is shown in the figure. The target T is so placed as to have its flight surface inclined at 45 degrees to the axis of the cathode ray stream and positioned at exactly the focus of the concave cathode C. The target T is made of metal having high melting point like tungsten, molybdenum, and platinum. The gas pressure inside the tube is maintained at about 0.001 mm. Induction coil is used to obtain the high tension as required to the tune of 30,000 to 50,000 volts. Arrangements are made to cool the target by a stream of water. The electrons constituting the cathode ray stream are produced as a result of ionization of the gas inside the tube. The production of X-rays by this technique suffers from certain limitations which are given as follows. Number 1. It is difficult to maintain the constant intensity and quality of the emitted X-rays for a prolonged period. Number 2. The walls of the tube gradually absorb the residual gas, and as such the intensity of the cathode ray stream gets reduced, as a result of which it becomes harder to operate the tube at the required tension. The Coolidge tube. Most of the drawbacks of the already described gas tube were overcome by Dr. Coolidge, who introduced a new type of tube, a modified one, which is now known by his name as the Coolidge tube. It is shown in a schematic diagram of figure 7.2. Filament of tungsten acts as a cathode, which is heated by a battery placed outside the tube at B. The filament emits thermionic electrons, which constitute the cathode ray stream. These electrons get accelerated towards the target T on maintaining a high potential difference between the filament and the target T. A very high vacuum of more than 0.0001 mm is maintained inside the tube. The highly accelerated electrons strike the target T and produce hard X-rays. A copper tube, which is fixed to the target T and gets projected outside the tube, is water-cooled. The high tension required is ordinarily supplied by a step-up transformer. The Coolidge tube has certain advantages over the above described gas tube. These advantages may be summarized as follows. Number one, the intensity of the X-rays produced is easily controlled by accordingly maintaining the filament temperature. Number two, quality of the X-rays produced can be conveniently controlled by designing the tubes which can be operated at high voltages ranging from a few hundred to 1 million volts, and operation of Coolidge tube is more stable in comparison to the gas-filled tube. There is, however, one disadvantage of the Coolidge tube, and that is the focusing of the electrons is not sharp, because almost the whole surface of the target has the tendency of becoming a source of X-rays. This disadvantage was overcome to some extent by making use of rotating anode tube. If different substances are required to be used as targets, detachable anode tubes are employed and put into operation. The modernized hot cathode Coolidge tube has been very useful to researchers on account of the fact that there is control over intensity and quality of the X-rays thus produced. The Betatron. Beams of energetic electrons are required for the production of X-rays. Betatron is an electron accelerator in which magnetic induction is used to accelerate the electrons. X-rays are produced by allowing highly energetic electrons strike the target by using a high potential difference between the filament and the target. There is another type of X-ray tube known as Betatron, in which electrons acquire high energy by using principle of resonance acceleration. The principle is also applied in cyclotrons. Figure 7.3 shows an arrangement for accelerating electrons in a Betatron. Capital M represent the pole pieces of an electromagnet connected to the alternating source of high voltage. The AC source, that is the alternating current source, is adjustable to the desired frequency. Capital VV is a vacuum tube in the shape of a ring which is placed between the pole pieces of the electromagnet. Capital S-S represents the solenoids wound around specially designed pole pieces of the electromagnet. The electron injector consists of heated filament, capital F, which acts as a source of electrons. Grid, symbolized by capital G, which is used for focusing electrons, and plate, represented by capital T, which is used as injector, shield. High potential difference is maintained between capital T and capital F so as to send electrons at very high speed into the vacuum tube, VV. The magnetic field between the pole pieces of the electromagnet acts parallel to the axis of the vacuum tubes. The electrons injected into the vacuum tube experience an electromotive force tangential to the electron orbit caused by the changing magnetic flux, which provides an additional energy to the electrons. Figure 7.3 shows accelerating chamber in a Betatron. The electrons also experience a radial force because of the actions of the magnetic field, which acts at right angles to the motion of the electrons. These two factors maintain the motion of electrons in a circular path. With the help of solenoids SS, the magnetic field at the center is so adjusted as to allow the electrons to move in a stable orbit of constant radius. The electrons are made to go through several thousands of revolutions in their fixed orbit, while the alternating magnetic field increases in intensity from 0 to a maximum value, which occurs during 1/4 of a cycle. Each of these revolutions provides additional energy to the electrons. The intensity of the alternating magnetic field gets maximum at the end of the quarter cycle. There are two coils of wire, one of which is placed above the stable orbit and the other below it. These coils are connected to a condenser which is discharged at the end of the quarter cycle in a manner that the electrons get switched out of their circular orbit so that they strike the back of the injector shield T, resulting into production of energetic X-ray beam. The shield thus acts as the X-ray target. The relationship between the linking flux and the magnetic flux is derived as follows. As said, the electrons are made to move in a circular orbit of constant radius in the vacuum chamber, which gains energy by induction caused by the change with time of the magnetic flux phi linking the orbit. The induced voltage per turn is given by d phi by dt. The electric field, that is voltage per unit length, is given by capital E equal to 1 upon twice pi capital R into d phi by dt, which we shall call as equation number 7.1, where capital R represents the radius of the stable orbit. The electron experiences force as is given by small e into capital E. The equation of motion for the electron is given by d by dt of mass into the velocity mv equal to small e into capital E is equal to small e by twice pi capital R into d phi by dt, and we shall call this as equation number 7.2. In order that the motion of electron in a circular orbit of radius capital R is maintained, the magnetic field capital H at the orbit has to be increased as the energy of electron increases. Capital H into small e, small v equal to small m into small v square upon capital R. Or we can say m into v is equal to small e into capital R capital H. Or d by dt of mv is equal to small e into capital R dh by dt, and we shall call this as equation number 7.3. In order to obtain acceleration of electrons by magnetic induction at constant radius capital R, equations 7.2 and 7.3 should be equal. That means d phi by dt is equal to twice pi into capital R square into d capital H by dt, which will be equal to 2 the time derivative of pi R square H, which we shall call as equation 7.4. The equation 7.4 states that in any time interval, the linking flux phi is required to change at a rate twice that which would occur if the central magnetic field were uniform and equal to the field at the orbit. This is the condition for a Betatron to function. In order that this condition is met, the Betatron is required to have a central iron core with high flux density inside the orbit. The cycle of acceleration in a Betatron is shown in figure 7.4. Electron gun is used to inject the electrons into the chamber at an instant when the magnetic field just rises from zero in the first quarter of a cycle as illustrated in the figure 7.4. During this period, the magnetic field is increasing, which induces a potential within the vacuum chamber, resulting into increase in the electron energy. Being in a magnetic field, the electrons move in a circular orbit, which is maintained stable by the increasing magnetic field. The field strength keeps on increasing till it reaches the maximum value. After attainment of maximum value, the strength of the field decreases and the direction of the induced electromagnetic force changes, because of which the electrons get slowed down. At this stage, the electrons are pulled out of their stable orbit by discharging the condenser, because of which they either emerge from the apparatus or strike the target T, resulting into generation of X-rays. The Betatron, however, suffers from a disadvantage. It needs a very large magnet so as to be able to provide variable flux, which is necessary for accelerating the electrons. This advantage is overcome by employing electron synchrotrons. One such electron synchrotron facility at Massachusetts has a 50-ton magnet and a radio frequency of 56.5 megacycles. It produces electron energies of the order of 330 million electron volt. Now we shall talk about detection of X-rays. X-rays have gained a lot of importance on account of their characteristics, which include the following. X-rays ionize gases through which they are passed. X-ray penetrate through matter. X-ray affect photographic plates. X-rays produce excitation and produce fluorescence in some substances. These characteristics of X-rays become helpful in their detection. Now, ionization of gases. On passing X-rays through a gas, secondary corpuscular radiations are emitted by the gas. The radiations so emitted are composed of fast-moving electrons. These high-speed electrons are striking with the atoms or molecules of the gas, produce positive and negative ions, thus making the gas conducting, which leads to an ionization current. The ionization current so produced depends on the rate at which the ions are formed. Greater is the intensity of X-rays, higher is the rate of ion formation. Therefore, measurement of ionization current can be used to quantitatively measure the intensity of X-rays. Ionization chambers are used for the measurement of ionization current. The ionization current, IC, is in the form of a hollow metallic cylinder which is closed at both the ends except for a small window W as is shown in figure 7.5. A sheet of aluminium is placed over the window W. YZ is the central electrode in the form of a rod inside the chamber. Figure 7.5 shows a schematic diagram of an ionization chamber. The central electrode, located on the axis of the chamber, is supported by a suitable material that keeps it insulated from it. Quadrant electrometer or a very sensitive gold leaf electroscope QE is connected to the suitably insulated rod YZ for measurement of ionization current. B is a battery whose one terminal is connected to the chamber, which is a hollow cylinder, and the other is earthed. In order that there is no leakage from the walls of the chamber to the central electrode, guard ring G is used. The guard ring is connected to the earth as is shown in the schematic diagram of figure 7.5. Suitable gas, usually at atmospheric pressure, is filled in the chamber. Suitable gases used for this purpose could be any of these that include air, ether, vapor, hydrogen, air, carbon dioxide, sulfur dioxide, or methyl bromide. For soft X-rays, sulfur dioxide gas is considered to be suitable, while for hard X-rays, methyl bromide is found to be the suitable one. X-rays are made to enter the gas chamber through the window as is shown in the figure. The X-rays ionize the gas and it becomes conducting. Since there is an electric field established between the chamber and the central electrode, the latter gets electrically charged at a particular rate, which is measured by the electrometer, capital Q dash capital E. The rate of charging depends on the intensity of the X-ray beam. The principle is applied in the measurement of X-ray intensity. The rate of charging can be determined by measuring the deflection of the electrometer needle for a given time. The ionization current is usually of a very small intensity, of the order of 10 raised to the power minus 13 amperes. Very delicate instruments are used to measure it. Sensitive electrometers are available which can measure the ionization current of this intensity. Interaction between X-rays and matter. X-rays are characterized by their strong penetrating power. There are two types of X-rays: soft X-rays and hard X-rays. Soft X-rays have small penetrating power and so can be easily absorbed by matter, whereas the hard X-rays have higher penetrating power. Let I0 represent the observed intensity of an X-ray beam incident normally on the absorbing material, and I the intensity after the beam has traveled through a thickness, say X, in the absorber. The intensity of the beam on traveling through this thickness will decrease. Let Di be the decrease in the intensity of the beam while traveling through a small distance dx of the absorber. Then minus d by dx is the rate of decrease of the intensity. It may be assumed that di by dx is proportional to I. Then minus d by dx is equal to mu I, where mu is a constant which is called the absorption coefficient. Or di by I is given by minus mu dx. On integration, it gives log I equal to minus mu x plus c. When x is equal to 0, I is equal to I0, which gives constant of integration C equal to log I0, or log I is equal to minus mu x plus log I, or I is equal to I0 e exponential of minus mu x. It suggests that the absorption phenomenon of X-rays appears to obey exponential law. That is, as X increases, I diminishes exponentially. The absorption coefficient mu of any given material is determined by finding that thickness X, which reduces the intensity to half of the initial value. That is, I by I0 is equal to exponential of minus mu x, which is equal to 1 by 2, or mu is equal to log 2 by x. If x is measured, its value can be used to calculate the absorption coefficient mu. If mu is small, the rays are hard and have great penetrating power. If mu is large, the rays are soft and as such are readily absorbed. The absorption coefficient mu depends on the absorbing material and on the radiation, but is independent of the initial intensity of the X-rays. The equation already given is true only for homogeneous X-rays. Radiation coming out of ordinary X-ray tube are heterogeneous because with increase in the thickness of the absorber, the value of mu decreases and so does not remain constant. As such, the above said equation does not hold for heterogeneous X-rays. Heterogeneous X-rays are those which consist of both hard and soft X-rays. If a beam of primary X-rays is made to strike a plate, some part of it goes through the plate and the remaining is consumed into generation of heat or any other form of radiation. The question arises as to what becomes of the radiation which is removed from the incident beam. The absorbed portion gives rise to a complex phenomenon known as secondary radiations. The secondary radiation coming out from the plate is comprised of characteristic X-rays, scattered beta rays, and characteristic beta rays. Figure 7.6 shows various types of radiation coming out of the plate when primary X-ray beam strikes the plate. Figure 7.6 shows transmitted X-rays and secondary radiation out of primary X-ray beam when it strikes the plate. The characteristic X-rays are so named because these depend upon the material of which the plate is made. Besides being homogeneous, these rays exhibit the same properties for a given element, irrespective of the hardness of the primary beam. The elements in general exhibit two kinds of characteristic radiation which differ in the value of their absorption coefficients. These are called K and L radiations. The K radiation is relatively harder as compared to L radiation, the absorption coefficient of the former being much smaller than that of the latter. The hardness or softness of the X radiation is determined by the value of absorption coefficient. Smaller the value of mu, harder is the radiation. This holds true for both K as well as L radiations. The characteristic radiation of the elements show increase in hardness with increase in their atomic weight. Diffraction of X-rays. Diffraction of X-rays is known to be historically the first technique which made study of internal structure of crystals possible. X-rays are a radiation of smaller wavelengths as compared to visible light, a wavelength of nearly 1 angstrom being X-ray wavelength. The spacing between the atoms within a crystal is almost this order of magnitude. The radius of an atom and the separation between two neighboring atoms on an average is also this order of magnitude. Real crystal is a three-dimensional array of atoms, and on exposure to X-rays, one finds diffracted X-rays coming out in all directions from every atom. It is because of this complication that one gets involved in three-dimensional geometry in an attempt to work out interference conditions. The only few particular and specific directions from which to view the crystal so that the diffracted X-rays are in phase and add up to give a strong beam so as to get recorded in the form of spot on a photographic film, plate, or with the help of ionization chamber or counters. These specific directions will depend on A. the arrangement of atoms in the lattice, and B. the wavelength of X-rays. In a crystal, there are atoms arranged in rows along the directions of its three crystallographic axes. It is this characteristic of X-rays that made it a very useful technique in the study of the internal structure of crystals. In 1912, von Laue, in collaboration with Fadderik and Knipping, discovered that crystals act as gratings suitable for the diffraction of X-rays. They allowed a beam of X-rays from an X-ray tube to pass through a thin crystal of ZnS, that is the zinc blende. The transmitted beam was allowed to fall on a photographic plate P. It was observed that the photographic plate got affected, and in addition to a central black spot at C where the direct beam struck the plate, there were several other spots in a regular pattern, suggesting that the X-ray beam incident on the crystal had got diffracted by the crystal planes. These spots were given the name Laue spots. The experimental setup is shown in a schematic diagram of figure 7.7. Figure 7.7 shows Laue experimental setup for diffraction of X-rays. The Laue experiment proved that the X-rays are electromagnetic radiation of definite wavelength. The atoms of a crystal are arranged in a regular pattern. Now let me explain Bragg's law. Laue's work on X-rays showed that crystals act as gratings for diffraction of X-rays. The diffraction does not take place because the wavelength of ordinary X-rays is somewhere between 10 raised to minus 8 and 10 raised to power minus 9 centimeter, while the average interatomic distance in a crystalline solid ranges somewhere between 10 raised to power minus 7 and 10 raised to power minus 8 centimeters. Also, the atoms or molecules are arranged in a regular repeating order, because of which some crystal symmetry is observed. We are familiar with diffraction of visible light by optical grating. Here too, diffraction of X-rays occurs when they strike a crystal. The crystal acts as a source of parallel reflecting planes. We therefore consider a series of parallel rows in which the atoms are regularly arranged, and each row representing planes of the crystal are placed at a distance d apart. That means the interplanar spacing is small d. Planes with interplanar spacing small d are shown in a schematic diagram of figure 7.8. Figure 7.8 illustrates Bragg picture of X-ray diffraction as in-phase reflections from crystal planes of interplanar spacing d. Let a train of monochromatic X-rays of wavelength lambda strike the crystal such as to be incident on the plane at a glancing angle theta. When X-ray beam falls, the atoms become centers of disturbance and spherical wavelets whose envelope results into a reflected wavefront. Since X-rays have a large penetrating power, it is necessary to consider reflection from several planes. So we have reflected wavefronts from each of the parallel planes. If these reflected wavefronts are all in the same phase, they will reinforce each other and the reflection gets exceptionally strong. The reflections are said to be in phase. However, if the incident angle theta does not satisfy the condition required for different reflections to be in phase, the latter interfere with one another and the resulting beam is weak. The required condition for the reflected wavefronts to be all in the same phase is that the path difference between the reflected wave from one plane and that from the next should be either an exact wavelength or an integral multiple of it. This is what we know from optics. We shall consider here two parallel rays AB and DE which get reflected by two atoms B and E in the adjacent planes along BC and EF, E being just vertically below B. The ray DEF has a longer path to travel ABC. The reinforcement of reflected rays with each other will and produces a brighter spot only if the path difference GE plus EH is equal to n lambda. GB and HB are perpendiculars drawn from B on DE and EF respectively. But GE is equal to EH is equal to BE sine theta, which is equal to D sine theta. So n lambda is equal to 2D sine theta. This is popularly known as Bragg's law. N is an integer. Now suppose the difference in path length is equal to one wavelength and then there will be a reflected beam at the position theta 1 which satisfies the Bragg condition lambda equal to 2D sine theta 1. This beam gives the reflection or spectrum of the first order. However, if the difference in path length is 2, 3, 4, etc. are wavelengths, then reflections of the second, third, -rth orders will be observed at the positions theta 2, theta 3, theta 4, etc., theta r. The von Laue equations. By allowing high-speed electrons to strike a metal target anode, X-rays can be produced. The wavelength of X-rays is of the order of 1.24 angstroms or 1.24 into 10 raised power minus 8 centimeters, which is just of the order of interatomic distances in actual crystals. According to Bragg equation, and lambda is equal to 2D sine theta, diffraction effects are observable for appropriate values of D and theta. Bragg assumed that a system of crystal planes could act and reflect X-rays, provided the conditions for constructive interference between reflections from successive atomic planes are satisfied. Let us consider two individual atoms, say capital A and capital B, and take into consideration X-rays scattered from them. Here capital A and capital B are the two identical scattering centers which are separated by a distance small r, as is shown in figure 7.9a. Figure 7.9a shows scattering of X-rays from scattering centers capital A and capital B. N0 represents the unit vector in the direction of the incident beam, which is assumed to be a parallel beam, and N1 represents the unit vector in the direction of the scattered beam. Path difference between the radiation scattered at capital B and that scattered at capital A is BC minus AD equal to R dot N0 minus R dot N1, which is equal to R dot brackets N0 minus N1. We shall refer to this as equation number 7.1. The vector N naught minus N1 is equal to capital N is normal to Bragg reflecting plane. Figure 7.9b shows a relationship of the incident and diffracted beams, scattered normal and the scattering plane. From figure 7.9b, it becomes clear that the magnitude of the vector capital N is capital N equal to twice sine theta. We shall call it as equation number 7.2. Let the phase difference between the radiation scattered at two centers capital A and capital B be denoted by phi. The phase difference between 2 pi by lambda times the far difference. One may put the phase difference between the radiation scattered at 2 points as phi equal to twice pi by lambda equal to R vector dot N vector. We shall call this as equation number 7.3. Now the condition for direction N to be at diffraction maximum is that the contribution to scattering from every atom in the crystal in that direction must differ in phase by an integral multiple of twice pi radians. To satisfy this condition, it is necessary for the radiation from atoms separated by primitive lattice vectors A, B, and C to add in phase, because in that case the contribution from other atoms separated from the origin by integral combinations of these vectors will add in phase. If contributions towards scattering from the neighboring atoms happen to differ in phase in some other form, there would be then always possible to have an atom somewhere in the crystal which would contribute radiation pi radians out of phase with the contribution from a given atom, ultimately leading to cancellation of these contributions atom by atom, giving no diffracted beam. Thus we will require that an integral multiple of 2 pi be got in equation 7.3 when R equals A, B or C. In other words, it is required to simultaneously have twice pi by lambda into A vector dot N vector equal to twice pi NH, twice pi by lambda B vector dot N vector equal to twice pi NK, 2 pi by lambda C vector dot N vector equal to twice pi NL. We'll call all these three as equation 7.4. Let alpha, beta and gamma be the angles between the scattering normal N vector and A vector, B vector and C vector axes of the crystal respectively. Then as per equation number 7.2, A vector dot N vector is equal to AN cos alpha, which is equal to twice A sin theta cos alpha, and so on. Therefore, equation 7.4 is written as twice A sin theta cos alpha is equal to NH lambda, twice B sin theta cos beta is equal to NK lambda, twice C sin theta cos gamma is equal to NL lambda. We shall call all the three equations as 7.5. The set of equations 7.5 are called Laue equations. Equations given as number 7.5 are a set of three equations which would determine the particular value for theta and capital N. That unique value of theta and capital N will provide the scattering direction. Equations 7.5 also suggest that the direction cosines of the scattering normal N vector are proportional to H by A, K by B, and L by C. Considering neighboring planes with mirror indices HKL and intersecting the A, B and C axes at intervals A by H, B by K and C by L, the direction cosines of the normal to the HKL family of planes are also proportional to H by A, K by B and C by L. The scattering normal vector n is therefore identical to the normal to the plane HKL planes, which means that the HKL planes could be regarded as the reflecting planes of the Bragg picture. If we set H equal to A cos alpha by D, K equal to B cos beta by D, and L equal to C cos gamma by D, each of the L equation of 7.5 can be shown to lead to Bragg equation L lambda equal to 2D sine theta, where D is the distance between adjacent planes of the HKL system. So students, let us summarize what we have learned in this module. We have learned about X-rays, their sources, and their interaction with matter. Description of gas tube, Coolidge tube, the Betatron is given. Various means of detection of X-rays are explained. The interaction between X-rays and matter has been described and explained. Diffraction of X-rays by crystals is discussed. The Bragg's law and von Laue equations are derived. Thank you.